Hi, this is Dr. Sheets. Hope you're having a good day. Today I'm going to talk about Chapter 10, Transaction Management and Concurrency Control. These are critical topics in databases because all big systems have multiple users, and multi-user transactions are, and controlling that process of making sure that each transaction does what it's supposed to do and leaves the database in a consistent state, and then and how to do that in terms of record locking or row level locking is what we're going to talk about today. So how to ensure multi-user access to our database is our topic. Well, so what is a database transaction, or what are database transactions? What does concurrency control really mean, and how does it help to maintain our database in a consistent state of integrity? And then what are locking methods and how they work? And I will say that this is some of the worst problems that I've ever encountered in industry were associated with deadlock resolution. Well, then we'll talk a little bit about time stamping, which sounds like the perfect idea, except it carries a lot of baggage. And then a couple other ideas of how to do concurrency control. And then finally, we'll talk a little bit about how recovery happens when a crash occurs. Well, the idea with a transaction is that it's a series of statements that are going to do some sort of task. And that task is make changes to the database of some sort. So maybe we have a customer that has a new invoice, and what we're going to do is insert the invoice to invoice line and then update the product table to show that what items were sold. That activity has to occur. All of it happens or none of it happens, right? If you get to the end and you can't update the product, do you really want to have that invoice line that points to that product that you couldn't access? And then an invoice that points to an invoice line that points to a product that doesn't exist. So you would want that not to be in your database. You would want neither the invoice line or the invoice to be in the database if you couldn't actually finish the job of updating the product. And that is sort of the idea of a transaction. It's one logical idea, unit of work that has to happen to the database based on some activity or event in the world. And we want to, and we need to keep it all together. And so to maintain the integrity of our database, we use things called transactions. In database transactions are not the same as user transactions. Now, I just sort of made the link to the user idea of an invoice line and buying a product and that stuff, but the time that a user transaction, if you're thinking of using the website to purchase a particular group of products or something, the time that you're out there on the website searching and all that, that's not the transaction, right? And when you put something in your shopping cart, that there hasn't been a real change to the quantity on hand, probably, right? Because anytime you have a transaction and it makes a change, and that change is somehow wrong, then what you have to do is do another transaction to correct that change. Like if you didn't roll back and you made a change, right, then you have to have a new transaction. So this is what we're going to talk about today. So this is how, using this idea of this unit of work, this transaction, is how we make sure that the things that change the database happen in an order that they're supposed to happen in. And I think you'll see as we go through that it makes total sense. So our goal is to take our database from one consistent state and put it into another consistent state after the transaction is performed. That means that prior to the start of the transaction, we already have a consistent database state because the previous transaction just committed. And then the next transaction starts with a perfect database. And then whatever it does has to be completed and return the database to its state of integrity. It can't put things like an invoice where there's no customer, things like that. So now the database is clean again after every transaction, and every transaction takes a microsecond, right, or some very, very short time. It's not like that the transactions there are many transactions involved in a user interaction with the database, because every select is also a transaction. It is a read transaction rather than a write transaction. So there's lots of transactions involved in that user session, but the actual purchase transaction, and from the database perspective, only happens at the very last instant, and is, like I say, just a microsecond. So most transactions do multiple things, have multiple SQL statements. It's of course possible to have them be a single statement, but they're usually multiple ones. So here is sort of an overview idea. Here we have a customer. You recognize this as an ER model. We have a customer with many invoices, an invoice with many lines. Let me get the highlighter. An invoice with many lines. Each line is for one and only one product. Each product is supplied by one and only one vendor. Now, if you think about it, whenever you sell a product, you have a new invoice for a customer. Right? You're going to have a new instance of invoice. Then you're going to have a new instance of line for every product code that you are going to have on this invoice. So they're like, here we have, it could be one invoice has many lines. Every instance of line has to be associated with a product code in product. Right? So if you think about a transaction for an invoice where, I'm going to Cabela's and I'm buying a fishing rod, a fishing reel, and a fishing lure, right? I'm going to have 3 lines. I'm going to have a new invoice, and I'm going to have 3 lines in 3 instances in line. And then I'm going to have to update the quantity on hand in product code for each of the products that I purchased. So the idea of a transaction is you want all these things to happen. You want the instance to happen in invoice, the multiple instances to happen in line, and the update to product quantity on hand, either all to work or all to fail together. That's the way we keep our database in consistency. Well, not all transactions have to update. They could be read transactions. Anything that accesses the database is a transaction, and it's going to need to be managed to make sure that the data that it retrieves, if it's just a read, is the correct data. And so if we have a bad transaction, or if we somehow design a transaction that doesn't have a proper ending, right? It doesn't end with a commit or doesn't end with a rollback, then we have problems, because then what's going to happen is the database won't be in consistency before the next transaction starts, and then that transaction's commit will cause a commit for all of the previous undone things. And so it's important to think about your transactions. And, this is part of what we do when we are writing our programs. If you looked at our next section.asp from the online survey system, you'll see that it has a number of transactions in it, where the perfect example is where it tries to see if the current participant is a new participant or not, and decide whether it needs to make a new instance of participant in case this person is new. And so it then will also create once it creates a new instance of participant, it'll then create a new instance of participant survey. Right? There's an idea of a transaction that's got to be completed before the actual survey starts. And if somehow you don't, if it fails in the middle of that process, then there can be a problem with the integrity of the database. Excuse me. Here's another sort of view of what the transaction is doing. So we have to have a row in invoice for our new invoice, and then we have a new row in line, and that row in line points to this product code 89WREQ, I think. I got my glasses on, but it's a little hard to see. And so you can see that what has to happen here, and I guess we're going even further to say, although these transactions aren't necessarily related to each other, I was noticing that in their ER diagram that their account transaction doesn't go with their customer, or doesn't go with their invoices, so they don't really know which account transaction goes with which invoice. They just know they received a payment. But so that's the idea of a transaction. All the work that has to happen to complete everything for the transaction, right? And I guess here, right, so you can see that this is the customer number that goes with this invoice, right? So they're coming down here and also updating the customer balance. And let's see. And I think they should have had this box here moved down one to the 277.55 so that those matched. I think that's just an error in their slide. But you get the idea. These are all the things that happened for the transaction of buying this product, which is a 16-inch high-cut chainsaw. And so, right, this is the idea that we're thinking about with the transaction. We need to make sure that all of the rows that need to be updated in this one logical unit of work are completed. And then once they are, then we issue our commit statement. And if anything fails anywhere along the way, we want to do what's called a rollback statement, which means remove anything that we've done. And this is the way the database is kept in integrity by using transactions. And that's, part of our job now that we've, designed our database, now that we are actually implementing our processes, our programs. Now it's our job to design our transactions so that they're efficient and complete. And this takes a lot of attention to detail to think about what are all the steps. But usually you'll be able to see it there's usually a transaction or a series of transactions associated with use cases. Well, there's several properties of transactions that are really important. The first and most important is atomicity. And that means that each transaction must be its own unit of work. And it must either complete or fail. It is separate from all other things. It must be its own thing. And it must be completed or it must roll back. It must either put the database into a new consistent state, or it must leave it in the prior consistent state. And that's what consistency is. The permanence of the consistent state. The database must always be consistent. And so the new transaction either has to leave it in a new consistent state or restore it to the prior consistent state that existed before it starts. Isolation is the idea that transaction can't be interfered with by any other transaction. Once a transaction starts modifying data, no other transaction can modify that data. It gets to operate in isolation on the data that it has, that it needs to use. Durability is the idea that once a transaction is committed, it'll never be undone. Once a commit occurs, the database is in a new consistent state. And so those changes will never be able to be undone. Now you can do a new change that changes the value of something that you changed before. But that change is never going to be undone. So let's say that you added 10 to the quantity on hand of a product, but it was the wrong product. What to do? Well, you have two things you have to do. The first thing you have to do is undo the thing you did. But since that transaction was committed, you now have to do a new adjusting transaction to make that product be 10 units less, because you mistakenly added 10 units to it. So it's a new transaction now. You can't, that's going to do it. The old transaction is already done and committed, and other work has occurred. So the new transaction changes that value. And then, of course, you'd have to have the correct transaction that set the value of the right product that you wanted. But durability is that idea that once it's in there forever. And all you can do is adjust it rather than undo it. Well, serializability is the idea that if we put the transactions in order as they modify the database, and if each transaction provides the consistency, meaning that it always leaves the database in a consistent state, whether it is in the prior consistent state before the transaction started, or whether it is in the transaction state after the transaction has changed the data that it needs to change. Either way, it's consistent. So what we want to do is serialize our transactions so that they occur in order and maintain the database in an always consistent state. And this is the key issues on transaction properties, and you're guaranteed to see questions like this about these concepts on the exam. And multi-user databases always have concurrency. I mean, I guess you don't have to think about Amazon. How many people are shopping right now and are about to hit the database? But there's some other little details to think about as we go on, and hopefully you'll see that it's not all gloom and doom. Well, the way that we keep our consistency is with the commit and the rollback statements. We've already seen those in our chapters on SQL, so you already know what they are. The transactions must either end in a commit or a rollback. And, I guess if an end of program is reached, you could have an auto commit kind of statement there. But if the program, well, maybe this has been fixed over time, but it used to be if you didn't issue a commit, if somehow your program ended, that was still open until the next transaction committed, and that was a real problem. Of course, we turned our auto commit off in our production database so that if anything happened, there would be no commit whenever the program ended. Of course, if you ever had a program that aborted, like to the command line or something like that, you had a real problem in our role. But we did a big deal. We did a lot of sophisticated error handling, so that never happened. But it's commit and rollback are the way that we maintain our consistency. So if you think of your programming languages, what you're going to have is you're going to have really probably only one way to the commit statement. But you're going to have a number of ways of going to rollback. Right? Now think, anytime you have an error, what do? You throw in an exception. Right? Well, anytime you throw an exception, part of the exception handling should be rolling back any transactions that are not committed at that point. Any data change activities that are not committed at that point. Well, the transaction log is the tool we use to know what happened, so that when something happens, we can then do it again in the exact same order that it happened before, and be ensured that our database, when we're finished doing our recovery, our database will be in the exact same state as it was at the time of failure. And so this is the only purpose of this log is to be there ready in case of some failure. And so then the idea is we're going to track through this transaction log and go back to a prior backup of the database that has everything in a consistent state. Like say we backed it up the first thing in the morning, and then we had an error at 2 in the afternoon. Right. So we would go back to that backup of the morning, and then we would go through the transaction log, and there's the DBMSs have built-in facilities for handling this. So then we would go back and then apply all the transactions from the transaction log to that clean version of the database we got from the morning backup. And then by 2:30 or whatever, we would have our database restored to the perfect state of data integrity that we had before the error occurred. And then we would have to change that error transaction and then apply it. Or that's not really, we don't do this for error transactions. We only do this in case of system failure. Right? So now we get up to the point where the system failure occurs, and we can then be ensured that from there forward we will be as completely consistent with the database before failure. Well, concurrency control is how do you let multiple transactions get to the same data? I mean, there's a chance it's going to happen, right? We're both at Cabela's, or maybe how about we're both at Zappos if you're not a Cabela's fan, and we both, well, that's probably unlikely. I don't know what they have at Zappos that we could both go for. Maybe a toppy hat or something. And it just so happens that we're both trying to update the quantity on hand at the exact same instant. Well, someone has to go first and someone has to go second, right? And that's what concurrency control is about, is managing that access to the data of multiple users at the same time. And so we use serializability to make sure that our transactions are ordered in a way that they all will leave the database in a state of consistency. But this is, so what we have to do is we have to take all our transactions and serialize them. And of course, since you've never had to worry about this, there must be somebody out there doing this for you. And it turns out there is. There's a thing called a scheduler, which we'll talk about in a minute. Well, so this is how it's supposed to work, right? So here we have two concurrent transactions, T1 and T2. T1 is going to purchase 100 units, and T2 is going to subtract 100 units. So in our perfect world, T1, it reads the current quantity on hand of 35. It adds 100 to that quantity, and then it writes that quantity, and then it commits and ends. Now comes along transaction 2. It reads the new value of the quantity on hand, 135. It subtracts off the 30 that it is purchasing, and writes back the new value of 105. Everything is both hunky and dory. Right? Transaction 1 executed completely, did all the things it was supposed to do in the order that it was supposed to. And then comes along T2 in the next serial order and does its task. The database was in integrity before T1 and after T1, and before T2 and after T2. But problems can occur if we don't ensure this serializability. And so let's take a look at some of those problems. Well, you can have what's called a lost update. And that is when two transactions update the same value, but they're not serialized in a way that maintains the integrity of the database. So one of the updates is lost when the transactions are completed. There's also a problem if we allow a transaction to read data that isn't committed. What can happen is the first transaction, if we allow the second transaction to read data from the first transaction, even though it's not committed yet, that's like a little looser rule, right? Being more permissive. But then that first transaction rolls back. Now the second transaction is using data that never existed in the database, really. It never was truly committed. It never reached that permanent state. So you can see that T2 in this case has a problem, right? It's using bad data. And then there's also a situation where we could be accessing data multiple times and end up with different data. And that is a problem also. And so let's look at these problems in more detail. Well, so here you can see that T1, this is our adds 100 to the amount, right? So then comes along T2, subtracts that amount off. Well, if before T2 starts, T1 is rolled back, then that 100 never got in there. If this quantity on hand is less than 30, then this number is going to go below 0. And it's just this idea of the this number, this quantity on hand, which should be, we had our previous slide. You saw, you might have remembered it was 35 was the number, right? And so what we're saying here is this was rolled back, but this quantity on hand here was already set, already added to be 100. So now when you subtract 100 or 30 off of it, you're going to have 105 left, but really in real life, you should only have 5 left, right? Because the 100 was rolled back. Well, lost update is a little more interesting. So here we have T1 makes a read of the quantity on hand. The value is 35. And then T2 also makes a read on the quantity on hand. So now T1 does its mission. It adds 100 to 35, the quantity existing quantity on hand. Well, then T2 comes in and does its task, right? Notice that T1 hasn't written its value yet. It has read. Now it's performing its operation. It's getting ready to write. And then, and so T2 did its read. Now it's performing its operation. So now comes along T1 writes, and it writes the value of 135, right? Because it read 35 and added 100. But then comes along T2, which writes its quantity on hand. And remember, T2 read also 35. It never saw this 100. And then subtracted 35 minus 30 and writes back 35. This value, the correct value, is totally lost because our transactions aren't serialized the way they should be. And that's the idea of a lost update. And that can only happen if you don't serialize your transactions. And this should show you why they should also be isolated. No data that is used by one transaction should be allowed to be used by another transaction while the first transaction is underway. Well, with inconsistent retrieval, it's the idea that a transaction is accessing data twice. And somehow you allow a second transaction to get in between those accesses and change that data. And so there's a chance that the data that you have, if you read the exact same data twice, a lot of times you might do another read for more rows as opposed to reading for an actual data value. But it's possible you could get a data value, a different quantity on hand for the same product, just because you read it at 2 different times, because you didn't have your transaction isolated, right? Because other transactions were allowed to read data. And, there's a reason that we allow these other transactions to read data, because even though these database transactions happen in microseconds, there's so many of them that the longer we have to wait, the slower our performance is. And so if we can allow people to read without actually hurting them, or hurting the accuracy of their data, then we would want to do it if we could. All right, so imagine this transaction. Here we have a transaction T1 that is making a sum of the quantity on hands of the product. And here we have T2 that is updating some particular products. Depending on when T1 accesses the data, it's going to get 2 different sets of numbers. In the before set, these 2 rows that are updated by the transaction T2 would be at their prior state. if it gets the data afterwards instead of before, you can see that now they've been changed. There's been 10 added to this quantity on hand and 10 subtracted from this quantity on hand, right? So the numbers are different, just depending on when the data were accessed. And I think this shows you why serialization is so important, right? Why it's important that the transaction end so that the new data we can be sure that we have is correct, or the data that we get in our transaction is consistent and has integrity. Well, this is sort of the same idea, but down at more of a micro level. So here we have T1 reads the row for this product, then reads the row for the next product, then Q2 reads a row from a different product. It adds 10 to that product and then writes that new value back. Now comes along T1, reads that new value, but then it also reads the next value of 23. Right, 25 is the correct value after T2, and then it reads, the T1 reads 23, then T2 comes in, reads 23, changes 23, writes back the change to 13, and then T2 commits. Then T1 just goes on reading additional rows. So it has picked up bad data twice. It picked up bad data once, right? Because this data, where the correct value is 13, was picked up by transaction 1 as 23. And that shows you how these kind of things can happen, and hopefully convinces you why transactions are important, and why and how serializability and isolation solve all these problems. So what we need is a scheme, a way to schedule these things, make them serializable, and ensure the integrity of our database. Enter the scheduler, which is really just a program. And what it does is it looks at the operations that are happening with the transactions that are open in the database and tries to make it so that it ensures that the transaction execute serial as though they were the only thing happening at that time, so as though they were totally serializable. And you can see that there would be a lot of transactions that wouldn't interfere with each other. Right? If you're doing a scan of the customer file for customers with a high balance, and you are receiving inventory on the loading dock and adding products to inventory, those two activities don't involve any of the same tables, any of the same data. So those transactions are totally serializable because they don't share any of the same data, so they should be allowed to proceed in parallel, right, concurrently, because they don't interfere with each other. Now, there's lots of transactions like that, but what we have to do is focus on the ones where there are some issues of where things can get out of serializability, and we have to ensure it. And so what we come up with is this schedule that shows This is the way that things have to happen in order for us to ensure that transaction serializability is maintained across all of these different operations. Well, locking methods are how we control these things in large systems, and so it's all about isolating our transaction and being sure that they execute as though they are completely serializable. And what a lock does is it means that only our transaction can have the data. And that means other transactions, if they happen to want that data, are going to have to wait. Or some other process is going to have to be involved so that when we are working with the data, we are sure that we can make whatever changes we need to. Well, there's a lock manager that is the program that assigns locks, uses the schedule to decide what transactions are going to go in what order, and maintaining all of the locks that have to occur throughout the transaction process. Now, pessimistic locking is the idea that there's going to be a lot of conflict between transactions. Now, this is where I was saying a minute ago that there is no conflict between the transaction that is looking at the customer file and the transaction that is looking at the product inventory file down on the loading dock. So sometimes there is locking issues and sometimes there isn't. And we need to pay attention to the situations where there are, and manage them, and not worry. We don't have to worry too much about the cases where there's no overlapping data on two transactions. Well, how we decide to lock can make a difference, though. Right? Suppose what we say is, well, the only one person or one user at a time can use our entire database. We were just sort of talking there. Let's see, what was I was talking about how there could be two tables that aren't that since those two tables are used by different processes, one for the customer search and the other for the bringing products in inventory, I was sort of implying a table level lock, right? Because you could just lock the table, and there wouldn't be any waiting or anything because they're using different tables, right? So they would never interfere with each other. But imagine you said a database level lock. If you said a database level lock, that means that only one transaction at a time can use the entire database. So you can see that would be a lot more restrictive than if you had a table level lock saying only one transaction could use a table at a time. Well, that doesn't sound so good, especially like if we are Amazon and we have products, we're going to have more than one transaction able to use the product table at a time, right? Because there's lots of people that are buying different products. We'd want to use like a row level lock on the product table so that, if we have 1,000 concurrent users, and I'm sure Amazon's way over that, right? So that they could all update the quantity on hand on a different row of the product table if they were doing different products. Now, there would be some people probably that are buying the same product. The transactions are going for the same row, and then those would have to wait. But none of the ones that are looking for other rows in the table would have to wait. And I think row level locking is more common than any of the other levels. You'll never see database level locking. That doesn't make much sense. Field level locking, when you're getting down to saying we're only going to lock the quantity on hand field on the product table. I think that's a little bit rare too. Well, so here's the idea of a database level lock. So this orange box is our entire database. Once T1 locks it, regardless of if it's going for, if T1 is going only for this row in table A and no rows in table B, it doesn't matter. T2 has to wait, even though T2 could be going just for rows in, I guess that's a better example. T1 is only going for rows in table A, and T2 is only going to rows for table B, but T2 has to wait. It has to wait because T1 has the lock request for the entire database first. Obviously, this would lead to more waiting than is necessary, right? It's not necessary for T2 to wait in this case, right? Because it's working with table B, not table A, and there's no interference with T1, so why lock the entire database? Well, if similarly, here we have a situation where T1 obtains a table lock, even though it might be going only for this row. Even though the T2 would want to work with this row, since the whole table was locked, it would have to wait until T1 finishes working with this row before it could do anything with this row. Row level locking would allow these two transactions to occur at the same time. You can see that they're not actually interfering with each other at all. Well, so this is the idea of a page level lock. Now, this is a little more a little less likely that you'll be involved or have to think about page level locking. I mean, this is just the next level down, right? Where you're looking at the disk page instead of the entire table. I think you'll see this as rare. Row level locking is the thing I think you'll work with the most. And so here what you have is T1 wants to lock row 1. And it's locked, it does its work, and then it ends its transaction. But T2 wants to lock on row 2. So it gets its row, it does its work, it's unlocked. So there wasn't any waiting in this situation. Right? No one had to wait because they were going for different rows in the table. And we are using row level locking. So T1 locked row 1 and used it and then released it. And then T2 locked row 2, then used it and released it. And this is how, by being aware of what the transactions are trying to do, this is how the scheduler makes sure everything is serializable. Right? Make sure that things happen in the right order to maintain the consistency of the database as though the transactions were applied one at a time without any concurrency. Most of our lock discussions are about binary locks, whether it's two-state, whether it's locked or unlocked. If it's locked, a transaction has total access and exclusive access to the data, and no other transaction can use that data. And so that is our basic way of thinking about locks, because it's just easier. And so, but it's not necessary to have everything be exclusively locked so that no transaction can can get any of the data. Suppose it's just reading the data, and we might allow it to continue. But we also have these shared locks where if it's not a problem for either transaction, then you might as well let them go ahead and complete. There's a lot of times reads will be okay, and not necessarily have to wait. Well, so here's the perfect binary world, right? We obtain a lock on product, we read, we perform an operation, we write, and then we unlock. And then the next transaction locks, it reads, it does an operation, and then it writes and it unlocks. And this is nice and simple, but I think you should be able to see that if this was read product ID 111, and this is read product ID 222, then there wouldn't be, these things could operate at exactly the same time and not interfere with each other. They would be as though they were perfectly serialized as they are here. But they could be operating in parallel with row level locking rather than table level locking, which would make T2 wait for T1. Well, it's possible that some schedule could be defined that isn't serializable, and it would have to be rejected. At some point, you can always go back to a stricter serialization schedule and cause more waiting and slower execution if you need to, but usually that doesn't happen. The scheduler, like the optimizer, are programs that run in the DBMS. They've evolved quite a ways, but it's still possible to have what's known as a deadlock, and that's when two transactions are going for the same data. All right, so let's see. We'll have a look at that in a second. So the way we get away with this is we have a two-phase locking protocol. And so what happens is a transaction acquires the locks that it needs before it does any of its operations. So if we think back to our transaction with the invoice, right? You obtain a lock on invoice, obtain a lock on line, obtain a lock on product. Right? Now that you have locked all of the tables that you need, now you can then do your work and then unlock those tables. Well, this is nice, but it doesn't really eliminate the possibility of deadlock. But it has the two phases. One is the growing phase, which is what you do as you get ready to do your work, making sure you've reserved or locked all the data that you're going to need, and then the shrinking phases as you release your locks. Well, the idea is that you can never have two transactions that are trying to lock the same data. That is a rule, and we'll see a deadlock here in a couple of minutes. So for any one transaction, no unlock procedure can come before a lock. And that means that you have to, before you can do any unlocking, you have to be done with all of your locking. Right? You have to have reserved all the rows and all the tables that you're going to change before you unlock any of them, before you do any operations or before you unlock. And there's the key idea. Until all the locks are in, you're not going to make any real changes to the data. So here's the idea. Over time, we step along and we acquire a lock on invoice, then a lock on invoice line, then a lock on product. Now we're at this point where we're locked and we're in this locked phase, and so we can do whatever work we need to do. And then once we've made all of our changes to our tables, then we can release our locks. This all happens by the lock manager, all behind the scenes. Although you can get some interesting views of what's happening in terms of locks from the Oracle console. Well, so a deadlock is when two transactions wait indefinitely for each other to unlock their data. It's also known as a deadly embrace. And what it means is that T1 has locked data that's needed by T2. But T2 has locked data that's needed by T1. So T2 has to wait until T1 releases their data, releases a lock. But T1 has to wait until T2 releases the lock on the other data. So we are at a impasse. No one can decide who's going to quit first, right? And that's sort of what has to happen. Someone has to stop waiting so that the other transaction can finish. And that's a real big problem. Like I said, this was our biggest problem in like our first 6 months of our billing system. Every now and then it would go into a deadlock. And finally we figured out that we had a commit out of position in our code. Basically, it was one transaction that was rare. When it occurred, it would leave open the database, so to speak, and not commit itself. And then another transaction would come along, commit, or one would come along and roll back. And then there would be a contention for those locks. And then once we figured that, it was a problem of our code that caused it. And so you'll know when it happens because everything stops on the database. At least that's what happened in ours, and I guess because it was on a critical transaction. And so we're going to have a series of things that we can do. We can try to prevent them. We got to detect them. And then with our coding techniques, we can try to avoid them. And the one that I know of was just one that was bad code. So here's the basic idea. All right, so the lock status is beginning. We have two data elements, X and Y. In the beginning, they're both unlocked. Data X is unlocked. Data Y is unlocked. T1 makes a request. Here we have time. So T1 makes a request, and then it makes a request at time T1, and then at time T2, the data for X is locked by T1. Now at time 2, T2 requests a lock on Y, which is also locked. Right? Now at time 3, now we have T2 has locked Y. Now come along, and remember, T1 is still locked because it was locked at time 2, so it's still locked at time 3. So now comes along, T1 wants to access Y, but it's already locked by T2. So T1 has to wait. because it has already locked part of the data that it wants, X, but it needs another piece of data, Y, but it has to wait because it's already locked by someone else. Well, so now T2 comes along at time 4 and wants to put a lock on X. But X is already locked by T1. So now we start to sort of get into this ugly little sequence of lock request by T1 for Y, and you have to wait because it's locked by T2. Lock request T2 for X, but you have to wait because locked by T1. And once you're there, it's never going to end. It's just going to take resources, and the system will be down. And you will be called by the customer in not a happy state. Well, you say, okay, I just fixed this. I just decided neat timestamp every transaction. That'll give me my order, all of my transactions. I'll be guaranteed that each one will be unique. No timestamp will be the same. I'll be able to know that I'll always be able to do it in the proper order. I'll always be increasing over time, so that when I restore my transactions, I will know that I've maintained my consistency. It'll be great. Oh, wait a minute. You know, there's always compromise in computer science. Everything is a trade-off, right? Problem here is once you start adding timestamps, you're adding a lot of data. If you think about some of the tables that we've designed in our ER diagrams, they're very simple tables. So if you start timestamping, you're increasing dramatically the amount of memory that you need, the power of the computer and the operating system that you need to make things work. So there's a cost to timestamping. So that's why we have some other techniques. And you know, one of them is the sort of the one that we've been talking about, is the wait and die, right? And so T1 comes along, and it waits until T2 has released all of its locks. If then if it doesn't do anything until T2 dies, and then T2 is rescheduled, but then and so T1 continues to wait. Well, if T1 comes along and T2 has a lock, but T1 can do in a wound wait scheme, T1 can preempt T2 and roll it back. And then T2 then waits until T1 is completed, and so releases its locks. And these are just ways in which we're trying to come up with some way of managing concurrency, but still maintain performance. Right? The problem we have with our concurrency is it causes slow performance because of waiting. Even though the time waited are microseconds or really short, this is the major impact, or has a major impact on performance. Well, we can also just be optimistic and say, listen, there's not going to be many transactions that are actually in conflict in this database. Because if you think about it, on the invoice table, there's almost no conflict, except whenever someone's coming back to protest or return something from an invoice, right? Because every action on the invoice table for that transaction is an insert, right? There's no reason to wait. There's no chance that another user, another transaction could have your data because it's an insert. You're making that data for the first time, right? If it's not an update or delete, right, there's no real chance of conflict. So if you think of the line table, right, you insert new lines for every invoice. There's no conflict there. Now, updating the quantity on hand in the product, as we've seen, right, has a potential for conflict. Well, so if you're going to do this, right, now you've really freed up a lot of resources. You have no locking or time stamping overhead, but you still have the problem of you have to maintain the consistency of your database. And so whenever you have a problem, right, whenever you have to check to be sure that before you write that the changes are going to maintain integrity and consistency of the database, right? So there's a step in the optimistic approach. There is this little validation step that occurs right before you do your write and make your changes applied. So there's a check process, but most of the time the check is really quick and easy. Right? There's nothing to check because there's no conflict between this transaction and other transactions in what they're trying to do. Something like the insert into a table, right? If you have many things but they're all inserts, there's never any chance of conflict. So there's no need to have locking on that particular set of transactions. Well, knowing what level to allow is, I guess, a little bit difficult to decide. But I think mostly what you'll usually find is that on all of your really important systems, you'll be doing a true serializable approach to all of the tables that have really important data to the organization, right? But there's some reports and things that you can run on a less restrictive level and allow things to be read, whether the data has actually even been committed yet or not. And you see here this idea of trying to be able to support faster reading and ignore some of the locking issues is something that's, people are aware of, and they want to provide resources to get the data out, right? But if you're Oracle, your number one most important thing is maintaining the consistency and integrity of your database. Well, recovery is the idea that at some point there's going to be a failure, right? And what we need to be able to do is we need to be able to take our transaction log and step through it one transaction at a time, right? Remembering every transaction is atomic, which gives us the ability to do this, that if we apply the same transactions in the same order, then we will end up with the database in the correct state. And so if you imagine that some system failure happens, right, then we have to go back to some backup of the system and then apply the transactions in the same order that they occurred during the regular operation before the crash. Well, some of the things that we do, the most important thing we do is we do transaction logs. And what we also may do some updating of the data as we go. It's possible to to update some of our data. Usually we use a deferred write process because we don't really want to make changes to the database until we are sure every transaction completes. But if we keep track of it, we can come back and allow partial writing. But it just makes our process of recovery more difficult. Now, we almost always have a redundant transaction log on multiple disks, right? Because the only way we're going to be able to bring our database back into integrity is to start from a known point and then restore forward. Well, if we lose our transaction log, then there's no way we'll be able to, even if we have a known point, we won't be able to roll forward. We won't be able to take if we don't have the transactions that occurred, we won't be able to apply them to the database, and then we won't be able to bring it into the correct state. Well, a checkpoint is this place we create to what we can say is we are guaranteed at this instant that everything was correct, right? And so if we can restore our buffers and our data to this point, we know we'll be good to start from here and apply our transactions in this roll forward process. So it's a way of trying to make the recovery process faster. Well, in the deferred write technique, what we do is we only update the transaction log. And then after everything is complete, we commit the transaction. So when we want to recover, when we use this technique, what we do is we go back to the last checkpoint. If the transaction was committed before that, it's already been recorded in the database, and it is committed and can't be undone. If the transaction was committed after the checkpoint, when we come to it in the log, we re-execute that transaction. If we come to a transaction in the log that was rolled back, we just skip it. Well, in the write-through technique, that means that we are updating the database immediately when the transaction operations occur. And so this is a little more tricky to handle. But what we do is we have our DBMS, we have what we call an after image file, a before image and an after image. And so if the transaction occurred after the last checkpoint, we use a different set of values, the after image values, so that we can restore or re-execute the transaction to get it back to the correct state. And this roll forward process, this recovery, is all automated within the DBMSs. It's sort of like a window that you use as the DBA to conduct these operations, and they're rare. I don't know if did we ever have to recover our database? Yeah, it seems like we did once. We had a disk failure that we had to recover. Actually, I remember that we were wondering how well it was going to go, but it worked fine. Well, so here's sort of what a transaction log might look like, and you can see that as you are coming through here, there's you see the skip in the numbers 341 to 352, right? These are all for transaction number 101, but all the pieces, there's more stuff interleaved in here that we're not seeing. But the point is that this transaction, you know everything you need to know. You know the operation, you know the table, you know the row ID, you know the attribute, you know the value before the change and the value after the change. And so this is the kind of detail that is in the log. And this is why we're able to do a restore of the database based on the log. And then here's the idea. We have a checkpoint occurs at this point. That means all the transactions are committed at that point, and we've stored all of our buffers. It's a place where we can come back and start from here. And then when the crash occurs, right, we don't have to worry about transactions 101 and 106. Actually, we don't have to worry about 101, but we do have to worry about 106, right? Because it doesn't commit until after the checkpoint. So if we had to come back to this checkpoint, we would have to redo all of transaction 106. But transaction 155 would be okay. Well, since it would have committed, we would have to redo it. End of transaction commit. Well, transactions are really important in databases. I mean, it is the key idea that allows things to really work in a way that is physically possible. A lot of the stuff we look at in terms of the ER diagram and the relational model and those things are sort of really good for solving the problem. But to actually make the systems run, this kind of stuff is critical, right? And so automaticity, serializability, right? They're the key ideas that allow us to make this transaction idea work. Well, we have this transaction log. We use it to make sure that we can have all of our transactions execute in the order that we want. There's a cool program in the DBMS called the scheduler that takes care of trying to do this. It's a very important process and is, I think, relatively easy to understand. It just sort of takes a little while to, you have to spend the time to think through it, to understand that the goal is that our transactions are what allow our system to maintain consistency. And so it's really important that they have the ability to operate on their data without being interfered with. Well, we use two-phase locking to ensure our serializability, where the locks grow until all of the data that is needed is secured, and then the operations occur, and then the locks are released. The idea of a deadlock is when two transactions are waiting for this. They've locked data that are needed by each other, and so we have to have methods for controlling this. One method is time stamping. We have several other methods that are more common, like pessimistic methods and optimistic methods. Well, that's all I have for today. I hope you're headed off for a good day, and I will see you in the forum.